This video is for my Biology for Health Sciences majors. We are on Unit 3, which is about biological molecules. So in Unit 2, we talked about atoms and how atoms form bonds with each other to build molecules. Now we're going to talk about the most important and the most abundant molecules that build cells, and cells are the most basic unit of life. So remember that most life on Earth consists of communities of single-celled organisms, while large organisms like you are composed of trillions of cells. So patterns of atoms build molecules, and patterns of molecules build cells, and patterns of cells build you. So in the next series of videos, I will introduce organic compounds to you, and then we'll talk about the 4 most abundant molecules that make life. There's carbohydrates, there's lipids, there's proteins, and nucleic acids. So biological molecules are carbon-based. When we say organic molecule, what we mean is a carbon-based molecule. Now, why is carbon so essential to life? Carbon forms the backbone of biological molecules in part because of its geometry. It has a very stable geometry. So here is a carbon in this ball and stick model. You have a black ball is a carbon in the center. And remember, carbon makes 4 covalent bonds. So this is methane. It's making 4 covalent bonds, each one to a hydrogen. So that's methane, CH4. And so you'll see, because those electrons repel each other, those covalent bonds spread out equidistant from each other, giving carbon this sort of like a tripod look. And this tripod, this you can see this prism or, sort of like almost pyramid-like structure on the right here. That is very stable. And another important thing about carbon is the fact that it makes 4 bonds instead of, 1 bond or 2 bonds. It creates, it allows carbon to build this wide diversity of different kinds of structures, which accounts for the diversity of molecules that build living things. So it has a stable structure and a branching structure. That makes it a very good building block of life. And I want to remind you that these molecules that we're talking about exist in 3 dimensions, but we draw them in 2 dimensions. So you may remember when we were talking about how methane looks, we drew it like this: carbon, and then the hydrogen bonds. If we want to show how they're spread out equally from each other, we draw them, in sort of like a plus sign shape. When in reality, what you would see is this tripod shape in 3 dimensions. So there's some inaccuracies, that are kind of problematic when rendering 3-dimensional molecules on a 2-dimensional piece of paper. So let's take a look at that, because we're going to talk about when we're building these complex molecules on paper, like organic molecules, you want to be able to look at it and accurately understand what you're seeing on the page. So here, this is a picture on the left of carbon's electron orbitals when it's forming covalent bonds. So carbon would be in the center, and when it has all 8 electrons in its outer valence, when it has a full outer valence because of covalent bonds it's making, they spread out from each other like this. This is the shape of their orbital. So there's that tripod-looking structure there. And then here on the right, you see this tetrahedron, which more accurately helps you understand the 3-dimensional shape of carbon-based molecules like methane. And so sometimes these bonds will be drawn like you see here. So these solid versus dotted lines for the covalent bonds, those really help you see more accurately the 3-dimensional nature of these molecules, as opposed to what we usually draw, which is this, right? This plus sign. So just keep in mind that these molecules are 3-dimensional, but we're usually going to draw them like this just because it's easier. But in reality, they look more like this, or like this, or like this. Methane and other compounds that are composed of only carbon and hydrogen are called hydrocarbons. Examples of hydrocarbons are fuel for your car, right? It's just these carbon chains with hydrogens all around. Carbon and hydrogen have approximately equal electronegativities, remember? So these are non-polar covalent bonds that hold hydrocarbons together, which means that hydrocarbons are hydrophobic. They are water-fearing because in non-polar covalent bonds, you don't have a collection of negative or positive charges across the molecule. Everything's neutralized. The protons are all neutralized by the electrons because they're all evenly spread out, which means that there's no electromagnetic charge to attract water molecules. So water is not interested in hydrocarbons. Hydrocarbons separate out from water. They don't dissolve in water. Carbon with attached hydrogens can form chains of various length, and like I said, a variety of branching structures. So here's some examples of hydrocarbons. You have ethane, propane, butane. Those all show you that you can have hydrocarbon chains that vary in length. A chain of 2 carbons, 3 carbons, 4 carbons, or more. The 1-butene and the 2-butene shows you that you can have double covalent bonds in a hydrocarbon. The isobutane shows that you can have a branching structure. Butane and isobutane, these are isomers because they both have the chemical formula C4. They both have 4 carbons, so C4, and then how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So H10. And is this one the same? 4 carbons and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is also C4H10. But you can see that the arrangement is different in these 2 molecules, which will give them slightly different properties. These are also isomers because they have the same chemical formula. They have the same number of carbons and hydrogens. So it's C4H1, 2, 3, 4, 5, 6, 7, 8. So H8. And this is the same, 1, 2, 3, 4, 5, 6, 7, 8. See, so they're both C4H8, but they're slightly different from each other. So those are going to be isomers. You also have cyclohexane and benzene. Those 2 molecules show you that hydrocarbons can form not just branches, but rings. So you can get hydrocarbon ring structures. And a note, these are all fuels. Hydrocarbons are energy packed. There's a lot of energy contained in the bonds between carbon and also between carbon and hydrogen. So the unique properties of an organic compound depend on 1, the size and shape of the carbon skeleton, and 2, the groups of atoms that are attached to that skeleton. So we're going to be talking about functional groups, which are little chemical groups that have unique properties that can be attached to the carbon backbone of these organic molecules. All right, so here you see testosterone and estradiol. The first thing I want to point out is that you don't see a lot of carbons. This is shorthand, and we'll talk more about this in this video. Everywhere there's a corner that's unlabeled, it's a carbon. So these are all carbon, 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 carbon. Every corner that is unlabeled with an element is a carbon. Okay, and the same over here. These are all, oops, there's a carbon there too. These are all carbons that are unlabeled. And also remember that carbon always forms 4 covalent bonds. But you'll notice that that's not always shown. So this carbon here, it's a covalent bond is shown here, and here that's 2. It's forming 2 more covalent bonds because carbon always forms 4 covalent bonds. So there's a couple that aren't drawn, and you can just assume that any covalent bond not drawn is to hydrogen. Okay, carbon always makes 4 covalent bonds. Any bond you're not seeing drawn is hydrogen. Biologists get lazy. We get lazy. There's so many hydrogens and carbons in every molecule. We just don't draw them all. So you just have to get an intuition for that. So these are all carbon rings. This is testosterone and estradiol, which is a form of estrogen. There's a few different kinds of estrogen. So these are sex hormones. And they look almost exactly the same. If you look at the carbon skeleton is almost exactly the same. The only difference is this one's missing some double covalent bonds, right? But other than that, same carbon skeleton. But what differs are some functional groups. Here here. There's a difference there. There was a difference in the double bonds here. And there's a difference in this methane group, okay? And that's missing from here. So these seemingly minor differences obviously result in huge consequences. These minor differences between testosterone and estrogen, minor chemical differences, result in these dramatic differences between the sexes in some species. Male lions and female lions look entirely different. So these functional groups that are attached to the carbon skeletons are very important. So here's a list of some of the most important functional groups that you'll see in organic molecules, in biological molecules. So you have hydroxyl groups. We've talked a little bit about hydroxyl ions before when we talked about acids and bases. So there's hydroxyl groups, carbonyl groups, you can see here, carboxyl groups. Carboxyl groups have a hydroxyl and a carbonyl. So they're called, the name just blends the hydroxyl and carbonyl together for carboxyl. So these are 3 out of the 6 functional groups I'm going to show you. But I want to point out now that one of the most important things to determine about a functional group is whether it is hydrophilic, water-loving, or hydrophobic, because that is going to really dictate a lot about how a molecule behaves, whether it has hydrophilic or hydrophobic functional groups. Because remember, hydrophilic things can dissolve in the water of the cell. Hydrophobic things will not dissolve in the water of the cell. If you want to determine if this functional group is hydrophilic or hydrophobic, you're going to have to compare the electronegativities of carbon and oxygen, and of oxygen and hydrogen, and of carbon and oxygen here. So looking to see whether there is an equal or unequal sharing of electrons will be a clue as to whether a functional group is hydrophilic or hydrophobic. Remember, polar things dissolve in water. Okay, here's a few more functional groups. You have amino groups, phosphate groups, and methyl groups. Methyl is a little bit like methane, right? Carbon surrounded by hydrogens. Also, notice how many negative charges are on phosphate groups. There's a lot of electrons there. So these are all functional groups that you will see repeatedly throughout biological molecules, and you'll have to understand how they work and what their properties are. And we'll get into that as we go through our biological molecules in this video series. So there are 4 classes of molecules that are most important to organisms. There's carbohydrates, which we're all familiar with, lipids, which are things like fats. You're also familiar with those, proteins, and nucleic acids. The 4 classes of biological molecules contain very large molecules. We call them macromolecules. Macro means large, micro means small. So macromolecule just means very large molecule. They are also called polymers because they are made from identical or similar building blocks that are strung together in long chains. So poly means many, right? Like polyamory. Amor means love, poly means many, so polyamory refers to many loves, right? And a polymer is a molecule that's made up of many repeating subunits strung together. The building blocks of polymers are called monomers. Mono means one, poly means many. So a monomer is the individual unit, and the polymer is all those individual units strung together. And I like to use the analogy of a pearl necklace. So if a pearl necklace is a polymer, you could call it a polymer because it's made out of repeating subunits strung together. So if a pearl necklace is a polymer, the individual subunits would be the pearls. Each pearl is a monomer, and all the pearls strung together, all the monomers strung together, creates a polymer, which is the whole pearl necklace. So that's sort of how most biological molecules are. There are these repeating subunits strung together like pearls on a necklace. So monomers are linked together to form polymers through dehydration reactions. This is the type of chemical reaction that causes one monomer to link up through covalent bonding with another monomer. And then these polymers can be broken down. I mean, this is what happens when you digest carbs and fats. You break down these large molecules into smaller ones, releasing energy from them as you do that. So polymers are broken apart by hydrolysis reactions. So dehydration is when you lose water. And hydrolysis, so lysis means to break. So hydrolysis is to break with water. So what you'll see in the following slides is that in dehydration reactions, you link things together by removing water, by dehydrating them. And in hydrolysis reactions, you break them apart by inserting water. These reactions are mediated by enzymes. Enzymes are like little robot catalyst machines that build and break down things in the cell. All right, so dehydration reactions are not that complicated. So you have some biological molecule that's a monomer, one of the pearls in the pearl necklace, but they're not joined together yet. Now, these are supposed to be the same size. Let's do that. And I'm just going to draw it as a blob because it could be anything. It could be a sugar, it could be an amino acid, it could be a nucleic acid, it could be anything. It doesn't really matter. Now, most organic molecules, they're carbon-based. So most of this blob molecule that I've drawn is going to be carbon, but they have those functional groups. And one very common functional group in biological molecules is hydroxyl groups, which look like this, OH. OH is a hydroxyl group. So you probably have a carbon here, because this is probably a carbon skeleton in these molecules, and that carbon's going to be attached to a hydroxyl group, which are very common in these biological molecules. So here you have these monomers. These are monomers. And this is another monomer. Oops. Okay, monomer and monomer. All right, so how are we going to join these together? So a dehydration reaction is when you remove water to join these two molecules. So how are we going to make water? With the hydroxyl groups. So this hydroxyl group is going to break off from here. And this oxygen is going to join up. There's going to be a break between this oxygen and this hydrogen. This hydrogen is going to join up with this oxygen here, forming H2O. So H2O is going to leave. And remember H2O, water, is just a hydroxyl group and a hydrogen. So this hydroxyl group here came from over here, right? And this hydrogen here came from here, okay? So where does that leave us? So water left, that's the dehydration piece. But the whole point of this is to join these two monomers into a dimer with two, and then to keep doing this over and over again, adding more and more through dehydration reactions until you get a polymer. So let's look at what's left now for our little monomers here. Okay. So this hydroxyl group hasn't changed, but this one, the oxygen lost its hydrogen that it was attached to. Okay, so now it's attached to the carbon skeleton of this monomer. But remember, oxygen has to form two covalent bonds to fill its outer valence, because oxygen has two empty slots in its valence shell. So it has to form two bonds to fill its valence. It has to share with two other elements. This carbon from the carbon skeleton of this monomer has completely lost its hydroxyl group. Now, this carbon it always makes 4 bonds. So it was making 4 bonds before, but now one of those bonds has been lost because the hydroxyl group left. It's going to have to form that bond with something. So this oxygen needs one more covalent bond to fill its valence, and this carbon needs one more bond to fill its valence shell. So they form the bond together, and now they're both complete again. Oxygen is forming 2 covalent bonds, and the carbon here is now back to forming 4. So that's how a dehydration reaction links 2 monomers together to build a polymer, and it just keeps happening over and over again. So here is another monomer, and it also has these hydroxyl groups. You take H2O away, and that's going to cause this oxygen to join up with this carbon. So the pieces that are left behind bond together. The lost bonds are reformed with the remaining pieces, and that joins those monomers together. Now, these biological reactions will happen spontaneously, but not fast enough to be useful for a living organism. So you need a catalyst. A catalyst is something that makes the reaction happen faster. That's what enzymes are for. So enzymes catalyze this reaction. So enzymes catalyze dehydration reactions. Dehydration reactions. Enzymes are just little molecular machines that catalyze chemical reactions for the cell, for living things. Now, energy is contained in these large macromolecules, in these polymers. There's a lot of energy contained in there. And that's actually the purpose for a lot of them, is to store energy. So to release that energy, for the cell to use that energy, like when you eat a hamburger, it's filled with these polymers, and you extract energy from those polymers by breaking them down, by breaking them apart back into monomers, and that releases the energy from them. So building polymers is like charging a battery, investing energy, storing energy in a battery to use later, and breaking those polymers apart back into monomers. That's how you release the energy from the battery. That's how you use the energy that was stored there. So to break down this polymer, we have to reverse this process. And to do that, we need to add water back in. We need to insert water. So let's draw our polymer now. So we had these repeating subunits, whatever they are, sugar, amino acid, nucleic acid, doesn't really matter. And they were joined together by removing water, leaving only an oxygen to link them, right? On the ends, we still have the original hydroxyl groups because they didn't get removed to join up with another. That's why it's the end. So a hydrolysis reaction is going to take H2O and add the water in to break that bond apart. So how is that going to happen? Well, an OH is going to attach to one of these monomers, and the H is going to attach to the oxygen on the other monomer. So we're just reversing the process that we saw before. So let's see how that's going to turn out for us. So let's just draw these pieces. And these are joined by their oxygens. All right. And this has its hydroxyl group on the end. This has its hydroxyl group on the end. All right. So now we're going to put a hydrogen on the oxygen. So let's say we're breaking it here. So one of these hydrogens from the water is going to attach to the oxygen that will stay there. And then we have carbon here, right? So that bond was broken. The bond between this carbon and this oxygen was broken. So now we can have space to insert the remaining OH. So this was 2 H's. That was H2O, 1 O, right? So 2 H's and the O. This was the water molecule, right? And it's now been inserted between these two molecules to break them apart. So now these are two separate monomers. Actually, I'll just draw a solid line. And you can do that to each one of these to break them apart, and energy will be released. This is hydrolysis or hydrolysis. Hydrolysis. Lysis means to break. Hydro refers to water. So this is hydrolysis or hydrolysis reactions break apart polymers by inserting water. Hydrolysis reactions also require an enzyme to catalyze this reaction, those little molecular machines. There needs to be an enzyme that can bind there and also bind to water and like stuff water in there to force a reaction to happen between them. Otherwise, this hydrolysis reaction, it just won't happen fast enough to be useful for biological organisms without the use of an enzyme.